What's up, guys? So today we're back to another system design problem, and this time we are going to discuss about Ticketmaster. So Ticketmaster is something like BookMyShow that is used in India, or apps where we book tickets for an event or a movie or a show or a comedy show. Suppose Taylor Swift announces a new tour. The pre-sale goes live at 10 a.m. At 9:59 a.m., 500,000 people have their fingers crossed, hovering over add to cart. Now at 10 a.m. hits and the site crashes. Or it doesn't crash, but the queue shows 2 lakh people ahead of you. You have to wait 4 hours. And you finally get in, the seats you wanted are gone. You get an error saying your seats are no longer available and you start over. Now, this is one of the hardest distributed system product in consumer technology. Not because the average load is high, but because of 60-second window when pre-sale opens, you get a catastrophic traffic spike that can overwhelm any system not specifically designed for it. And unlike an e-commerce flash sale, there's an extra constraint, the fairness. If you got into the queue before someone else, you deserve to buy your ticket before they do. That's what Ticketmaster, StubHub, Eventbrite, BookMyShow grapple with every day. Let's design it from scratch. First, let me outline what this system needs to do in the form of functional requirement. First, event and venue management. Artists, promoters, and venues create events. They configure seat maps, ticket categories, pricing tiers, and sales schedules. Second, ticket inventory management. This is very important. The system maintains a precise count of available seats per section, per row, and per individual seat. Each seat has one owner at any point in time. The third, seat selection and reservation. Users browse an interactive seat map. They select specific seats. The system places a temporary hold, typically 8 to 10 minutes, while the user completes the purchase. Nobody else can book the same seat during the hold. Then, fourth is queue management for high demand events. For flash sales, users enter a virtual waiting room before the sales open. At sale time, users are admitted in fair order, generally randomized from the waiting room pool. The fifth is checkout and payment. User completes purchase with card and saved payment method. Ticket is confirmed when a barcode is generated. Then the sixth is barcode generation and ticket delivery. Each ticket has a unique scannable QR code or a barcode. Tickets delivered via email, app wallet, print at home PDF. Seven, the most important is fraud detection. In this AI world, fraud detection is very important. The scalpers use bots to automate purchases. The system must detect and block bot behavior. The eighth is resale marketplace. Ticket holders can list their tickets for resale. The platform takes a service fee on resale transactions. And the ninth is mobile ticket transfer. The ticket holders can transfer tickets to other users' account. If you want to transfer it to your friend or your relative, that functionality also should be available. After this, let's go into the non-functional requirement. This is also very important for an interview. Now, the hard requirements are traffic spike handling. On a normal day, Ticketmaster handles out 10 million pages views per day. When a major artist goes on sale, imagine Beyonce or Taylor Swift, the traffic can spike up to 100x to 1000x in seconds. The system must not crash. It must degrade gracefully. It's acceptable to make user wait in the queue. It's not acceptable to lose data or confirm duplicate bookings. Seat reservation consistency. A seat must never be sold to two different people. This is the core correctness requirement. Like hotel booking, like financial system, the hardest part is preventing double sell under concurrent load. That is fairness. The queue must be fair. First come, first served, or at minimum, randomly ordered among users who arrive from before sale time, not based on who has the fastest computer. Then we discuss about the latency. Seek map loads under 500 milliseconds. Seek hold confirmation under 1 second. Then checkout under 3 seconds. Then it should be an available system. We will discuss about availability. The system must stay available during the traffic spikes. we expect at least 99.9% uptime during the normal operations. Then the ticket integrity. A ticket barcode must be unique and unforgeable. These are some of the non-functional requirements that we need to put, and these are very important. After that, for a senior level, capacity estimation is very important. Let's size a Taylor Swift Eras Tour pre-sale scenario. Suppose the stadium capacity is 70,000 seats. The number of shows, say 50 shows globally. Total tickets for sale is 3.5 million tickets. Queue size at pre-sale open, let's say about 2 million users enter the waiting room. What about the request per second? At the exact moment when users are admitted, if we admit in a batch of 10,000 users every 30 seconds, we are generating about 500 seat page loads per second plus 500 checkout requests per second from active shoppers. That sounds manageable, but the real spike is in the waiting room that joins at T minus 60 minutes. 2 million users connecting in 30 minutes, which is around 1100 concurrent connections per second, ramping up. The system needs to handle 2 million concurrent long-lived connections. It could be in the form of WebSocket or polling. This is basically for the waiting room. Then what about the ticket inventory? There are around 3.5 million tickets to be sold. Each record can take up to 1 KB. That's about 3.5 GB of inventory, small enough to fit in the large Redis instances. Then the loading of per event seat map. At a venue of around 70,000 seats, it needs around 70,000 element data structure tracking state that will be available, held, or sold per seat. Then barcode generation, we need around 3.5 million unique barcodes that are needed for the sale. After this, we'll go into the API design. We'll discuss some of the important APIs. The first one is the Get Event Details API. This is used for getting the event details. It will be a get type. We will have the version number as V1 events and the event ID. This returns the event info, venue, date, ticket categories, on sale time, and remaining tickets. If we want to get the seat map, we will have an API with the events and event ID slash seat map. It will return the full seat map with the availability status per seat. If the response is very large, it will return in the paginated format. Then we have the join queue. If we are having people in the waiting room and they want to join, this will be the API V1 events event underscore ID queue join, and then the user IDs and the event ID. This will return the queue token, estimated wait time, and position in the queue. After that, there will be check queue position. What is the position of the person in the queue? So we can have V1 events, event ID, queue, and status. It will have an authorization bearer token that will be used for authentication. It returns current positions, estimated weight, and can shop and catch shop. Then there will be reserved seats for hold. We will have this API for V1 events, event ID, and holds. So this will pass the seat IDs that we want to hold, then the duration for the hold, that is around 600 seconds. It will return the whole ID, seats, total price, and expiry time. Once we confirm the purchase, this will be the API for purchasing. So it will have V1 hold ID slash purchase, and there will be a payment token, and there will be a delivery method, which is like a mobile app. This will return the order ID, ticket ID, and the confirmation number. And post that, there will be a release hold. If you want to release the hold, use the delete API for that, and we'll pass the hold ID. And it should ideally return the success or failure in case of negative. Now, if you want to list the ticket for resale, you'll pass a ticket ID and do slash resale. In that, we can put the asking price and the currency. This will be for the resale. This holds are all the functional requirements APIs. These are the main APIs, and we will start building around it. Here is the view of the data models. So some of the tables are the event table, the venue table, seat table, ticket inventory table, holds table, orders, then tickets table, queue table, and then we will have sorted set per event ID. The queue table, in queue table, that is Redis. This is not relational, but we will have sorted set for event ID. Then members, this will be a sorted set for user ID, and then a score. that will have a joint timestamp, and then the queue table, which is a part of the Redis. So these are some of the main table. Although there will be many more tables, these are some of the important ones. And this shows how these tables are related. You can take a snapshot of this table and put it in your notes if you want to discuss about it. But with this ER diagram, these are self-explanatory columns. I will not go into details about the columns. You can go through it offline. That is pretty simple at this level. After this, we will go into the high-level design. So let me walk you through the system architecture. First, we will have the CDN plus the edge server. All the static assets, the seat map images, venue photos, event pages served from the CDN. No origin hits for the static content. After that, we will have an API gateway. In the API gateway, we will have rate limiting, authentications, and the routing. The waiting room service, it manages the queue during the pre-sale. It holds the user in a lobby before the actual sales open. It also controls a rate at which the users are admitted into the shopping floor. Then we have the event service. Event service is for event and venue metadata, then seat map definitions. We have the inventory service. The inventory service, it tells the source of truth for the seat availability. It handles the holds and the releases. After that, we have the checkout service. Checkout service is responsible for orchestrating the payment and order creation. After checkout, we need to do the payment. So we will have a payment service. Payment service integrates the payment gateway. It handles authorizations and capture. After that, we want to deliver the ticket. So in the ticket delivery service, it will generate the barcodes. It will send you the mail and update the mobile wallet. We also want to do the fraud detection because many people are trying to get all the tickets in one go. So in that, you will have real-time scoring for the purchase request. It will rate it. What is the level of fraud in this? Then we have the resale marketplace service. It is used for listing, discovering, and purchase of resale tickets. After that, we'll have a notification service, which sends the confirmation email, reminders, and then transfer notification. The critical architecture decision. The inventory service uses Redis for state status and not a relational database for the hot part. Here's why. At peak, we need to handle thousands of concurrent seat hold requests. Each hold requires read current status, then check if it's available, and then atomically set it to held. And Redis, this is a single atomic command using the Lua scripting or Redis transaction. Postgres, this requires a row level lock, a read, and an update, which is an overhead. For a 70,000 event venue, the entire inventory fits into one Redis instance. Postgres is used as a durable store. Redis is the hotcast synchronized back to Postgres asynchronously. Let's do a deep dive in some of these components that will be used. Although you have to just discuss one or two, I'll go through all the components so that you get the knowledge about it. First is the flash sale traffic spike and the queue management. This is the most interesting architecture challenge in the entire system. Let's say a concert goes on sale at 10 a.m. By 9:45, 500,000 users are on the event page hitting refresh. At 10 a.m., they all click shop now, shop now, shop now simultaneously. If we let all the 500,000 users straight into the seat selection flow, we generate an instantaneous spike of 5 lakh concurrent requests to the inventory service. Even with great infrastructure, this will cause latency spikes, then the connection pool exhaustion, and likely cascading failures. The solution is a virtual meeting room. Here's how it works. Before the sales open, we redirect all the users to a waiting room page. When the user hit the waiting room, they get a queue token assigned JWT with the joint timestamp. The waiting room page polls or receives WebSocket pushes every few seconds with a queue position update. When the sales open, instead of releasing everyone at once, we release users in batches, say around 5,000 users every 30 seconds. The selection is random from within the pool of users who joined before the sales open. This is the fairness guarantee. Showing up early gets you into the pre-sale mode, not a specific queue position. Randomization within the pool prevents fast clicker advantage. Now, users who join after the sales get queue position based on the join time. This is strictly first come, first service. How do we implement it? Now, waiting room page is a static HTML page served from the CDN. So zero origin load. Now, the queue state lives in the Redis. The first one is the sorted set of the event, which has the pre-sale pool. It has all the members which are part of the pre-sale pool with the user ID, and the score is joint timestamp. This is used for pre-sale random selection. Then we have a sorted set for the event pool for the people who joined after the post-sale open. So this is queue for the post-sale. Then we have a key where we have the event ID and the admitted count. This tells how many users have been admitted so far. A batch admission job runs every 30 seconds. Let me describe it. At t is equal to 0, the sales open. Then shuffle the pre-sale pool using the Fisher Yates and assign new random scores. This becomes the randomized queue. Every 30 seconds, zpopmin event ID Q5000 gets the next 5000 users. For each user, issue an admission token. This is shortlet JWT token, which has an expiry time of 15 minutes. Then we notify the user via WebSocket that they can now shop. The admission token is essential. The inventory service requires a valid admission token on every hold request. Without it, the user cannot create holds even if they bypass the queue. This prevents the queue jumping via direct API calls. The next component we are discussing is seat reservation with pessimistic locking. When an admitted user selects a seat and we need to atomically hold those seats, in Redis, the seat status for each seat is a key. It will be like seat, event ID, seat ID, and the status. The status value can be available, held, or sold. For a hold request on seat A12 to A13, we use a Redis Lua script to atomically check that all the request seats are available. Then if any seat is not available, we abort them and return which seats are taken. If all of them are available, set all the seats to held with the hold TTL of 600 seconds and then return success. Now you might ask, why do we need Lua script? Because Lua script in Redis are atomic. No other command can execute between step 1 and 3. This is our pessimistic lock. But here's a principal engineer ask. Lua scripts in Redis blocks the entire Redis instance while running. For a large script, this can cause a latency spike. Then the solution is keep the Lua script minimal. Just check the status and set. The whole metadata like user ID, expiry, total price is written to the Postgres table. Now for single seat holds, the Lua scripts run in under 1 millisecond. And for 4 to 6 seats, it still runs under 2 milliseconds. That's quite good. Now, what about the hold expiry cleanup? Redis TTL automatically expires the status key after 600 seconds. But we also run the background check that scans the hold table for the expired holds. If the expired at is lesser than now and status is equal to active, it will explicitly free those seats both in Redis and the Postgres. The belt and suspenders. Redis TTL is the fast part. The cleanup job is the safety net. The next main component is the fraud detection. Scalpers are serious problem. They use bots to automate the entire flow. The join queue, get admission tokens, select seats and check out. Some techniques to detect and block them. First is captcha at admission. When a user is admitted from the queue, before they get into the admission token, they complete a captcha. Bots fail captcha. Human pass them in 5 seconds. This single step catches the majority of the naive bots. Then we do the behavioral analysis. Log the timing of the user's action, the page load, the first click, seat selection, then the checkout start. A human around takes 30 to 90 seconds to select the seats and the start checkout. A bot does it in the 3 seconds. Score each session on the behavioral time. Suspicious sessions trigger additional friction. Then we can put second captcha, email OTP. We can limit the purchase per account, maybe 4 tickets per event per account. Then we can limit the credit card usages, maybe 4 tickets per event per card. Or we can also do the device fingerprinting, 4 tickets per fingerprint. These limits are checked at checkout, not at the hold creation. Holding seat doesn't count against the limit. Only the confirmed purchases do. If you want to do the device fingerprinting, we can use JavaScript-based client fingerprinting. Libraries like fingerprint.js collect the browser attributes, install fonts, screen resolution, and generate the fingerprints. Now link the fingerprint to the past fraudulent purchases. Block the known fraud fingerprints at the queue entry point. We can do the velocity check. If an account attempts to purchase more than n times per hour, flag for the manual review. If a credit card is used for the purchases as multiple concurrent event, we can flag it. Now, a principal engineer can also question bots can randomize timing to mimic the human behavior. What do we do then? Then we can do network level signals. Look at the ASN. ASN is autonomous system number of the IP. Cloud providers like AWS, GCP, Azure are disproportionately associated with the bot traffic. Now, the purchase velocity across the platform, if 100 accounts are created in last 24 hours, all the purchase tickets to the same event within the 5 minutes are like a bot farm. We can do ML-based fraud scoring. Train a model on a historical fraud patterns, score in real time, then flag high scoring transaction for the manual review or a challenge. Then the next part is barcode generation ticket integrity. Each ticket has a unique, unforgeable QR code. The barcode encodes ticket ID, event ID, seat ID, and a cryptographic signature. Signature is usually HMAC SHA-256 encrypted, which has the encryption of ticket ID, event ID, seat ID, and the secret key. Then the venue scanner app verifies the code. It decodes the QR, verify the signature, and check the ticket is not already scanned, and then mark it as used. The uniqueness can be done by UUIDs for the ticket IDs. The probability of collision is very negligible in terms of UUID. Now, for preventing the counterfeiting, anyone who captures the QR code and prints it cannot forge a valid ticket because they don't know the secret key. Even if someone screenshots a QR, the scanner marks it as already used. Now, for mobile tickets, the QR code rotates every 30 seconds using the time-based algorithm similar to the TOTP. A screenshot of the QR is useless after 30 seconds. How do the venue scanners work at scale? For 70,000 person concert, there might be 50 scanners at station. Each station needs to be able to validate the tickets even if the network is slow. The solution is pre-distribute the event signing key to the scanner devices at the start of the day. The scanners can validate the signatures offline. Scan tickets IDs are synced to the central use ticket Redis set in real time. Duplicate scans are automatically flagged. If a scanner is offline for more than 5 minutes, it fails back to signature only validation without the duplicate check. We can accept a small risk of accepting one duplicate entry rather than blocking thousands of legitimate entries, right? Now, the next component we are going to discuss about the resale marketplace. The resale marketplace is essentially a second layer ticket exchange. Sellers list the ticket at the asking price. Then the buyers browse the listing and purchase it. We have the key decision over here. One is the anti-scalping measures. Some events are set with the fan-to-fan resale restriction. Tickets can only be resold at face value or up to the small premium of about 10%. These rules are stored per event and enforced at the listing creation. Ticket transfer on sale. When a resale purchase is confirmed, the system invalidates the seller's barcode and issue a new barcode to the buyer. This prevents the seller from retaining a valid copy. The original ticket is marked as transferred. A new ticket record is created for the buyer. The next part within this is the trust and the escrow. Sellers don't receive payment till the 48 hours after the event. This ensures that the buyer actually attends with a valid ticket before the seller can actually get paid. And this way, we do the buyer protection. If the ticket turns out to be invalid at the gate, the buyer gets a full refund and is offered comparable replacement tickets if available. Now, if you're interviewing for the staff level or a principal level, here are some of the questions which can be asked. Maybe we can take it in another session. I'll just give you a list of some of the questions. They can ask like the Redis-based seat inventory fits in a memory for a single event. But what about 10,000 concurrent events? How do we handle those? Then another question that can be asked is, what happens if the Redis goes down during a flash sale? Then they can also ask, how do you handle the situation where the user's holds expires while they're still on the payment page? This is also another problem. Question 4 can be, how do you scale the waiting room to a 10 million concurrent users for a global superstar? Okay, this one is a very important part because it tells you how mature are you in your thinking. What if some problem happens? For that, we do observability and monitoring. Now, for a flash sale system, monitoring is a war room operations. Your staff engineers are on call, watching dashboard live during the sale. The key metrics we want to measure are the queue metrics, the inventory metrics, the checkout metrics, the fraud metrics, the infrastructure metric, and the alerting. I'll give you a brief about each of the metrics. In the queue metrics, we measure about the queue depth per second. Then we measure admission rates, which tells the users admitted per minute. Then queue join rate versus the admission rate. Then we talk about the estimated time to empty queue. In inventory metrics, we can have some metrics like the seat held versus available versus the sold per event in real time. We also talk about the hold expiry rate per second, where the seats returning to the pool, then failed hold attempts, seats already taken. Then we have the checkout metrics. We measure here the checkout attempts per second, payment success rate, payment gateway latency P99, then the orders confirmed per second. In fraud metrics, we can talk about the CAPTCHA failures, account flags per hour, then IPs blocked per minute. Infrastructure metrics is also very important, where we measure the Redis memory utilization, the Redis CPU, the API gateway request and error rate, and the CDN cache hit ratio. Where we should alert immediately if the Redis available memory drops below 20%, if the payment success rate drops below 95%, if the seat hold error rate spikes above 5%, or the CDN origin pull rate spikes. Now, after this, there is very important issue of the data lineage. Nobody talks about the data lineage. How do we do the traceability? But it is very important. How do we map the data between different parts of the microservices? So we are going to talk about the data lineage here. So ticketing has significant fraud and dispute resolutions that are needed. For example, I bought this ticket, but it showed invalid at gate. What if I transferred my ticket, but the recipient says it never received? Or if I was in the queue for 3 hours and I got kicked out without being admitted. For each of these, we need a full log event so that the person can say, is it valid or not? So every state change for a ticket is an event. It can be issued, held, sold, transferred, used, invalidated, or refunded. The event log is append only and immutable. For a dispute, support can replay the entire ticket lifecycle. It has the correlation ID. Every user session has a session ID. The queue admission has a queue token ID. There is a hold ID, the order ID, or the ticket ID. These chain together like session, queue token, hold, order, and the ticket. A support agent can trace from the ticket invalid at gate back to who held the seat, when, and what payment was used. Now, if we do the queue audit log, we store every queue join event, every position update, every admission in a time series log. This is a defense against the queue was rigged accusations. Show users these queue join timestamp and the randomization methodology on request. All right, let me pull it all together. The core inside in a ticketing system is its concurrency and the fairness problem at its heart. The seat reservation challenge, that is atomically holding seats under thousands of concurrent requests, is solved using the Redis Lua script, and this provides atomic check and set. The flash sale traffic spike is solved using the virtual waiting room. We randomize the queue and the rate limited admission. We protected the inventory service from being overwhelmed. Now, fraud detection operation at multiple layers is happening. One is capture at admission, behavior analysis during shopping, purchasing limit at the checkout. We have barcodes for cryptographically signed and time rotating for mobile tickets to prevent screenshot copying. The resale marketplace integrates tightly with the ticket invalidation. Old barcodes are killed when the tickets are transferred. And for the every ticket state change, we maintain an immutable event log for fraud detection, dispute resolution, and compliance. The deepest insight here is about the controlled degradation. When a million user hits your system at once, you cannot serve them all simultaneously. The question is, do you crash or serve nobody? Or do you queue everyone and serve them fairly? The waiting room is not just a technical solution, it's a user experience decision. Users who understand that they are in a fair queue, even a 2-hour queue, are more patient than the user who hit a crash page. Now, building systems that degrade gracefully and communicate clearly is as important as the technical architecture itself. That's what we built today. Now, thanks for watching. If it was very useful, you subscribe to Yodama. See you in the next time.